Let's continue with a reader-writer problem. The reader-writer problem is another classic synchronization problem that arises when multiple processes need to access a shared database or a shared dataset or repository is accessible by multiple concurrent processes. And we categorize these processes as readers and writers. The challenge is to allow multiple writers, okay, more than one readers to access and read the data at the same time, while we want to ensure that only one writer has access to modifies the shared data at any given time. The key characteristic of readers and writer processes are that in reader processes, at any given time, a reader activity may express the intent to read data from the shared database, and multiple reader activities can access and read data simultaneously without causing conflicts. In the writer processes, similarly, at any point in time, a writer activity may wish to modify the data in the shared database. Unlike readers, writers need exclusive access during the writing process to ensure data consistency. So we observe simultaneous reader access and exclusive writer access and the dynamics of writers problem. Naturally, by allowing parallel reading operations, simultaneous reader access improves system efficiency. Additionally, we guarantee data integrity by preventing any other writer or reader from accessing the shared data while a writer is actively writing to the database. So the readers and writers problem shows up in several forms, each of which introduce new priorities, unique considerations, and preferences. Let's examine two popular versions, okay? In the first version, known as the first readers writers problem, okay? It's actually prioritize readers' immediate access unless a writer has already been granted permission to use the shared object. No reader should be forced to wait in this scenario. Okay, so readers are not restricted because of the presence of other readers. Rather, their access is based on the absence of an active writer. The second readers writers problem, on the other hand, emphasize the fast execution of a waiting writer. When a writer is ready to access the shared object, it is given priority, and no new uh, new readers are permitted to begin reading until the writer has finished its task. Furthermore, either solution to the problem may increase the risk of starvation. In the first case, writers may face starvation, whereas in the second case, readers may face starvation. Because of these concerns, alternative problem formulations have been proposed to address potential starvation cases. Now let's look at the proposed solution to the first readers writers problem. It's the solution for first readers writers problem. So it prioritizes the readers processes. So this solution introduces a set of mechanisms to address reader-writer concurrent operation issues when accessing a shared database. The followings are the solution's shared data structures. So read-write mutex semaphore is initialized to 1. It is used for writer mutual exclusion. This semaphore ensures that only one writer can access to the critical section at a time, and it avoids write conflicts. And this semaphore is also used by the first or last reader who enters or exits the critical section. And we also use mutex semaphore. When updating the read count variable, another semaphore with initial value of 1 is used to provide mutual exclusion. To ensure exclusive access to the counter, a reader must first acquire and then release this semaphore when incrementing or decrementing the read count. And read count is a counter which is initially set to 0, and it keeps track of how many processes are currently reading the shared data. This counter is required to manage the concurrence of multiple readers accessing the database at the same time. So the writer process is encapsulated within a do-while loop, indicating that it will perform its operations forever. This line indicates that the writer is using the wait operation to acquire read-write mutex semaphore. Okay, so this semaphore's purpose is to provide mutual exclusion for writers. If the semaphore is not used by another writer, the writer can proceed. Otherwise, the writer must wait until the semaphore becomes available, of course. So the wait operation decreases the value of semaphore, indicating that writer has now occupied the critical section. In the critical section between wait mutex and signal read-write mutex is where the actual writing operations take place. This is where the writer updates or modifies the database's shared data. In signal read-write mutex, after finishing the writing operation, the writer uses this signal operation to release its hold on the semaphore. This increments the value of the semaphore and indicates that the critical section is now open to other writers. And this code, it outlines the structure of the reader process. The reader process, like the writer process, it's encapsulated within a do-while loop, indicating that the reader will perform its operations indefinitely. So the first operation, wait mutex, is to use the wait operation to acquire the mutex semaphore. This ensures that updating the read count variable is mutually exclusive. After that, we increase the value of read count variable, which keeps track of how many readers are currently in the critical section. And in this line, read count is equal or not. This conditional check ensures that the current reader must wait on the semaphore if it's the first to enter the critical section. This mechanism ensures that if a writer is currently in the critical section, new readers will be forced to wait until the writer has finished its operation. And then we signal the mutex. So it releases the mutex semaphore, allowing other readers to concurrently update the read count variable. In between them, we have critical section, and this critical section where reading operations are performed between two mutex operations. Okay, wait mutex. Before updating the read count variable, we need to reacquire the mutex semaphore, and then we decrease the read count to indicate that the reader has completed the critical section, and the number of readers is decreased by 1 this time. And we have this check. If the current reader is the last one to leave the critical section, so it's when the read count becomes 0, this semaphore is activated. Okay. If there are any waiting writers, they will be given to access to the critical section. And at the end, we have signal mutex. Okay. After updating the read count variable, it releases the mutex semaphore.